Hello, my name is Niels Stressler and I'm an industrial PhD student from Atlas Copco within the LINK-SIC Center. Welcome to my presentation of the research on clamp force-based control for tightening processes of threaded fasteners. The research is focused around simulation-based studies and experimental verification. The general functionality of a threaded fastener in a threaded fastener joint is to clamp two or more parts together and keep them in place, even if external loads are applied. This is done by the so-called clamp force, which is a combination of the bolt extension and the joint compression. The clamp force achieved during tightening is subject to scatter, which is mainly due to the friction in the process, which is difficult to control. Therefore, we're trying to develop strategies that rather are based on the clamp force as a control parameter. In contrast to that, modern state-of-the-art tightening strategies are mainly based on torque and angle, or yield tightening, which itself relate to clamp force somehow, but as mentioned before, not very accurately. Our main challenges are to further develop methods to estimate the clamp force, or measuring methods to be more accurate than that. And then we want to base our tightening strategies on that. One of the main challenges we are working currently on is accurate modeling of the mechanics in the threaded fastener joint. We're trying to combine this with typically known models for the driveline or the involved motors and gearboxes. Our main objective is to be able to really have the clamp force in the threaded fastener as a state. When these models are finally developed, we plan a set of studies. One of the studies we're planning to conduct is the influence of friction variations on tool control, because we can assume that the friction is just known in a very rough manner, but simulate that the friction actually behaves like it would do in the actual process. Then we want to see how our control laws will be influenced by the changes in friction. In order to be able to verify the model, we are also currently developing a test rig, which is constructed in a very open way, but also contains the typical components of a tightening tool. The plan is to have a test bed where it's easily possible to prototype new control strategies and load them directly on the used controller. One of the first studies we conducted to find better methods to estimate the friction in the joint showed very interesting results when we applied Kalman filters to it. We used the extended unscented Kalman filters in order to estimate the friction which is in the joint. This means the friction in the thread of the threaded fastener and under the head. What you can see here is a state space representation of our system, with the different states for the angle, the angular velocity, and the friction as a state, which is very important because we want to estimate the friction in a better way. Further down, you also can see a discretization of the system, which we finally used to do the Kalman filtering. As mentioned, the study showed very promising results where the friction could actually be estimated with an error of less than 2%, which is compared to all known methods a very, very good result. We plan to further study the subject and develop algorithms which we in the long run want to implement on our test bed here, show if it really holds in practice. If you're interested in my research or have further questions, please feel free to reach out to me. Thank you for listening to my presentation.